In physics, statistical mechanics is a mathematical framework that applies statistical methods and probability theory to large assemblies of microscopic entities. It does not assume or postulate any natural laws, but explains the macroscopic behavior of nature from the behavior of such ensembles. Statistical mechanics arose out of the development of classical thermodynamics, a field for which it was successful in explaining macroscopic physical properties, such as temperature, pressure, and heat capacity, in terms of microscopic parameters that fluctuate about average values and are characterized by probability distributions. This established the fields of statistical thermodynamics and statistical physics. The founding of the field of statistical mechanics is generally credited to three physicists. Ludwig Boltzmann, who developed the fundamental interpretation of entropy in terms of a collection of microstates. James Clerk Maxwell, who developed models of probability distribution of such states. Josiah Willard Gibbs, who coined the name of the field in 1884. While classical thermodynamics is primarily concerned with thermodynamic equilibrium, statistical mechanics has been applied in non-equilibrium statistical mechanics to the issues of microscopically modeling the speed of irreversible processes that are driven by imbalances. Examples of such processes include chemical reactions and flows of particles and heat. The fluctuation dissipation theorem is the basic knowledge obtained from applying non-equilibrium statistical mechanics to study the simplest non-equilibrium situation of a steady-state current flow in a system of many particles. Principles: mechanics and ensembles. In physics, two types of mechanics are usually examined: classical mechanics and quantum mechanics. For both types of mechanics, the standard mathematical approach is to consider two concepts: the complete state of the mechanical system at a given time, mathematically encoded as a phase point, classical mechanics, or a pure quantum state vector, quantum mechanics. An equation of motion which carries the state forward in time, Hamilton's equations, classical mechanics, or the Schrödinger equation, quantum mechanics. Using these two concepts, the state at any other time, past or future, can in principle be calculated. There is, however, a disconnection between these laws and everyday life experiences, as we do not find it necessary, nor even theoretically possible, to know exactly at a microscopic level the simultaneous positions and velocities of each molecule while carrying out processes at the human scale, for example, when performing a chemical reaction. Statistical mechanics fills this disconnection between the laws of mechanics and the practical experience of incomplete knowledge, by adding some uncertainty about which state the system is in. Whereas ordinary mechanics only considers the behavior of a single state, statistical mechanics introduces the statistical ensemble, which is a large collection of virtual, independent copies of the system in various states. The statistical ensemble is a probability distribution over all possible states of the system. In classical statistical mechanics, the ensemble is a probability distribution over phase points, as opposed to a single phase point in ordinary mechanics, usually represented as a distribution in a phase space with canonical coordinates. In quantum statistical mechanics, the ensemble is a probability distribution over pure states, and can be compactly summarized as a density matrix. As is usual for probabilities, the ensemble can be interpreted in different ways. An ensemble can be taken to represent the various possible states that a single system could be in, epistemic probability, a form of knowledge, or the members of the ensemble can be understood as the states of the systems in experiments repeated on independent systems which have been prepared in a similar but imperfectly controlled manner, empirical probability, in the limit of an infinite number of trials. These two meanings are equivalent for many purposes, and will be used interchangeably in this article. However, the probability is interpreted, each state in the ensemble evolves over time according to the equation of motion. Thus, the ensemble itself, the probability distribution over states, also evolves, as the virtual systems in the ensemble continually leave one state and enter another. The ensemble evolution is given by the Liouville equation, classical mechanics, or the von Neumann equation, quantum mechanics. These equations are simply derived by the application of the mechanical equation of motion separately to each virtual system contained in the ensemble, with the probability of the virtual system being conserved over time as it evolves from state to state. One special class of ensemble is those ensembles that do not evolve over time. These ensembles are known as equilibrium ensembles, and their condition is known as statistical equilibrium. Statistical equilibrium occurs if, for each state in the ensemble also contains all of its future and past states with probabilities equal to the probability of being in that state. The study of equilibrium ensembles of isolated systems is the focus of statistical thermodynamics. Non-equilibrium statistical mechanics addresses the more general case of ensembles that change over time, and/or ensembles of non-isolated systems. Statistical thermodynamics. The primary goal of statistical thermodynamics, also known as equilibrium statistical mechanics, is to derive the classical thermodynamics of materials in terms of the properties of their constituent particles and the interactions between them. In other words, statistical thermodynamics provides a connection between the macroscopic properties of materials in thermodynamic equilibrium, and the microscopic behaviors and motions occurring inside the material. Whereas statistical mechanics proper involves dynamics, here the attention is focused on statistical equilibrium, steady state. Statistical equilibrium does not mean that the particles have stopped moving, mechanical equilibrium, rather, only that the ensemble is not evolving. Fundamental postulate. A sufficient, but not necessary, condition for statistical equilibrium with an isolated system is that the probability distribution is a function only of conserved properties, total energy, total particle numbers, etc. There are many different equilibrium ensembles that can be considered, and only some of them correspond to thermodynamics. Additional postulates are necessary to motivate why the ensemble for a given system should have one form or another. A common approach found in many textbooks is to take the equal a priori probability postulate. This postulate states that for an isolated system with an exactly known energy and exactly known composition, the system can be found with equal probability in any microstate consistent with that knowledge. The equal a priori probability postulate therefore provides a motivation for the microcanonical ensemble described below. There are various arguments in favor of the equal a priori probability postulate. Ergodic hypothesis. An ergodic system is one that evolves over time to explore all accessible states, all those with the same energy and composition. In an ergodic system, the microcanonical ensemble is the only possible equilibrium ensemble with fixed energy. This approach has limited applicability, since most systems are not ergodic. Principle of indifference. In the absence of any further information, we can only assign equal probabilities to each compatible situation. Maximum information entropy. A more elaborate version of the principle of indifference states that the correct ensemble is the ensemble that is compatible with the known information and that has the largest Gibbs entropy, information entropy. Other fundamental postulates for statistical mechanics have also been proposed. 3 thermodynamic ensembles. There are 3 equilibrium ensembles with a simple form that can be defined for any isolated system bounded inside a finite volume. These are the most often discussed ensembles in statistical thermodynamics. In the macroscopic limit, defined below, they all correspond to classical thermodynamics. Microcanonical ensemble describes a system with a precisely given energy and fixed composition, precise number of particles. The microcanonical ensemble contains with equal probability each possible state that is consistent with that energy and composition. Canonical ensemble describes a system of fixed composition that is in thermal equilibrium with a heat bath of a precise temperature. The canonical ensemble contains states of varying energy but identical composition. The different states in the ensemble are accorded different probabilities depending on their total energy. Grand canonical ensemble describes a system with non-fixed composition, uncertain particle numbers, that is in thermal and chemical equilibrium with a thermodynamic reservoir. The reservoir has a precise temperature, and precise chemical potentials for various types of particle. The grand canonical ensemble contains states of varying energy and varying numbers of particles. The different states in the ensemble are accorded different probabilities depending on their total energy and total particle numbers. For systems containing many particles, the thermodynamic limit, all 3 of the ensembles listed above tend to give identical behavior. It is then simply a matter of mathematical convenience which ensemble is used. The Gibbs theorem about equivalence of ensembles was developed into the theory of concentration of measure phenomenon, which has applications in many areas of science, from functional analysis to methods of artificial intelligence and big data technology. Important cases where the thermodynamic ensembles do not give identical results include microscopic systems, large systems at a phase transition, large systems with long-range interactions. In these cases, the correct thermodynamic ensemble must be chosen as there are observable differences between these ensembles not just in the size of fluctuations, but also in average quantities such as the distribution of particles. The correct ensemble is that which corresponds to the way the system has been prepared and characterized, in other words, the ensemble that reflects the knowledge about that system.